Hello students, welcome back to the channel. So in this video we are going to be handling the second part about differentiation. So this video is going to be specifically handling a subtopic of maximum together with minimum, together with its applications. So make sure that you like the video, subscribe to the channel and then share the video to your colleagues. Before we resume. So starting maximum and minimum, we are going to be handling them as three different components. We are going to have a maximum, which is a point on the curve represented by the tip of that curve. And then we have a minimum, which is going to be a point which is represented by the bottom of this curve. And then you're also going to have a point of inflection. Now, a point of inflection is going to be a continuing curve, whereby the curve does not go down. In other words, the curve is going to be going in one direction. So at this point, in the middle of that graph is what we call the point of inflation. So starting, we are going to select a point on a curve at which the gradient is 0. By gradient, according to the previous video, we say that gradient is the same as dy dx, or derivative of y in respect to x. So at any point, either maximum or minimum, or point of inflation, or is the gradient, or what we can call the dy dx, is always going to be equal to 0. And this is going to be known as the stationary point. So we are going to get stationary point, first of all, by differentiating our function of y. After getting dy dx, and then we equate our derivative to 0. And then the values of x that you get and also the values of y are going to be the turning points. And those turning points are either going to be maximum or minimum. Now a turning point is the same as a stationary point. For example, according to this curve, it's going to be point P. It's going to be that point at which the curve makes its peak. So we're going to say that a stationary point, the tangent to the curve is going to be horizontal to the curve, or what you can refer to as flat. So we have said that there are going to be three stationary or turning points. We have what we call the minimum point, and the curve is going to be going downwards. And also here, for us to get the turning point, we shall say that the derivative, which is dy dx, must be equal to 0. Now, we are going also to look at their nature after getting the stationary points, or what you can call the turning points. So let's first look at the maximum turning point. So if you observe this curve, if you are to name the maximum turning point, is going to be the point where the curve makes its peak. So for the maximum, it's going to be at the top. For the minimum, the curve must be at the bottom. And for the point of inflation, the curve must be in one direction. It can either be going this side, diagonally, or it can be coming from up to down. The curve does not change direction. That's what we call point of inflation. So looking at maximum point, we are also going to say that here also the gradient or dy dx is also going to be equated to 0. So proceeding, we are going to say that in this case the gradient of the curve is going to be positive to the left. Now what we mean here, this is going to be important when you are finding nature of the curve, and you're going to look at that under the examples. So we made a note that here the maximum and minimum points are also called the greatest or least values. For example, we may give you a function of y in an item or in a scenario or in a question, and then we tell you to find the greatest and least values. So greatest is going to be referring to a maximum point. Also at the greatest point, we refer the gradient to be equal to 0, which is the same as dy dx. Also the minimum point is going to be the same as the least value. And also at this point, dy dx must also be equal to 0. So looking at the example, we are going to start with finding coordinates of the stationary points. If at all we are provided with a function of y to be equal to x cubed plus 3x squared then plus 1. So we find the stationary points and then we distinguish between the two stationary points that we are going to get. So first we start by writing the function of y. So after writing the function of y, we find the derivative of y since we are dealing with stationary points. So remember that the derivative is always the same as the gradient. And then we say that the assumption is always going to be that at turning points, always the gradient, which is the same as dy dx, must be equal to 0. So we get our derivative and then we equate it to 0. Now we are going to use the factorization method and then we solve this quadratic. So it's going to be 3x into bracket of x plus 2. So the first value of x is going to be 0 and then the next value of x is going to be negative 2. So now here you have to remember that for us to get the turning point, we have to have the x value together with the y value. So for each of the values of x that we have attained, we get the corresponding y value. So when x is equal to 0, we get the function of y and then we substitute for x. And then we shall end up with the value of y to be positive 1. Then also when x is equal to negative 2, we substitute x into the function of y. And then we end up with the value of y being equal to positive 5. So we're having 2 points. We're having 2 turning points or 2 stationary points. We're having when x is equal to 0, y was 1. And also when x was negative 2, y was 5. So we have already got our 2 turning points. So this table is going to help us find the nature of our turning points because either of them has to be a maximum and the other one has to be a minimum. Or any can be a point of inflection. So this is the purpose of this table. Now let's look at what this table contains. So the first row is going to be containing the value of x. So what we do here, we simply write only values of x. So remember that you got x is equal to 0. We also got x equals to negative 2. Now, after writing them, on opposite sides of each x value, you must have the left-hand side, which is denoted by L, together with the right-hand side, which is denoted by R. We do the same on the other x value, left and right. So the reason why we do that is we want to get assumpted numbers that exist on the number line besides those x values. So if you look at the number line, on the left hand side of this number line, you're going to have negative 1 if you start from x equals to 0. And on the right hand side on the number line, we assume it's going to be positive 1. You just pick the numbers that you assume. Someone else can assume negative 2. Someone else can assume negative 3. For as long as it's on the left hand side of the number line when you start from x equals to 0. So I've picked negative 1 here and I picked positive 1 to be on its right hand side. So we do the same here. If you look at x equals negative 2, the number which is going to be next to it on the left hand side on the number line is going to be negative 3. So I'm going to put here a negative 3. And then the number which is going to be on the right hand side can be 0 or it can be negative 1. So let me go with negative 1. Now the second row is going to be constituting the sign of dy dx. So remember that our dy dx was the same as 3x squared plus 6x. So we get this value, we only want the signs that are going to be displayed if we substitute for the assumpted value that we put on the left hand side of this x value. So if you look at here, if you substitute negative 1, which we assumpted up here, into this equation, it's going to be 3. It's going to be 3 minus 6. And that's going to be negative 3. So the answer is going to have to be negative. So you put here negative. So here we don't do anything. You simply leave it blank. You don't write anything. Then on the right hand side, if you put here positive 1, you're going to have 3 plus 6, and then you're going to get positive 9. So if you substitute with positive 1, we are going to get a positive answer. So you only write the symbol of the answer that you are getting. Then you do the same thing here. So if you substitute negative 3 into this equation, it's going to be 3 times 9, which is 27, then minus 18. So you're going to get a positive, because 27 minus 18 is going to give you a positive answer. Then you also substitute for negative 1, which we assumpted here. If you substitute for negative 1, we have already seen here that you're going to get a negative answer. I hope that was clear. Now the third row is going to constitute of the nature of the curve. Now under the nature of the curve, here we strictly depend on the sign. If at all the sign is negative, you go down diagonally. If at all the sign is positive, you go up diagonally. So if you look here, we had a negative sign up here. That's why our curve is going down. So in this middle part, we don't indicate any deviation. So you just draw a straight line. Then, since here we're having a positive, you simply draw your graph going upwards. And that's how we find nature of a curve. We do the same thing to this x value. So here we started with a positive value. So we draw our curve horizontally going upwards. In the middle part, we don't do any deviation, so we just draw a horizontal line. And then the right value is negative. So you draw a diagonal line going downwards. For negative, the curve must be going downwards. For positive, you sketch going upwards. Now if you look at this curve, we have got two shapes. Let's also look at it up here. So you have got two shapes. If you look at the first shape, it's in this format. And the point, the x value that has given us that was the x value which is 0. So point of 0 and 1 is going to be the minimum point simply because it's the bottom of the curve. And then since this other x value gave us a curve which is in this format, that means that the other point of negative 2 to 5 is going to be our maximum value. And that's how we find nature of the stationary or turning points. So you're going to select, therefore the stationary point 0, 1 is going to be a maximum point, and then the stationary point negative 2, 5 is going to be a maximum point. Now one of them is minimum, this is going to be minimum point, and then this is going to be maximum point, according to the nature of the curves we got. So one was upwards, and the other one was downwards. The one which is downwards is the minimum, and the one which is upwards was the maximum, which is negative 2 and 5. Now let's look at another example. So with this, we are saying that find the coordinates of the stationary point for the following curve. So after finding these coordinates, we don't stop there. We have to find their nature. Are they maximum or minimum? So first, rewriting the function. After writing the function, we find the derivative, because whenever I ask stationary points or turning points, we have to find gradient. And how do you get gradient? By getting the derivative of the function that you are given. So if you differentiate function of y, you're going to get 4x cubed. And if you differentiate negative 4x cubed, you're going to end up with negative 12x squared. Then we bring in our assumption, which I missed out here, but you must include it. That at stationary points, the derivative must be equal to 0. After saying that, we get our derivative and then we equate it to 0. So we solve this by factorization method, and then we end up with 4x squared into x minus 3 to be equal to 0. So we are going to get the two values of x, one to be 0 and the other to be positive 3. So we say that for each value of x you get, you have to get the corresponding value of y, because always the turning points have to be more than 1. So when the value of x is equal to 0, we substitute x into the function of y, and then you're going to end up with the value of y to be also 0. Therefore, the first turning point that you're having is going to be 0 to 0. Then also when x is equal to positive 3, what's going to be the value of y? So we get the function of y, and then you substitute for the values, or for the two values of x. Then you end up with negative 27 after substituting everything properly in the calculator. So you're having two values. One of them is 0, 0, and the other one is 3, negative 27. But now we don't know their nature. We don't know which one is the minimum, and we don't know which one is the maximum. So we have to draw our curve. So we say that the first row is going to constitute of the value of x. So one value of x that we had was x equals to 0, and the other value of x that we had was x equals to 3. And then, besides or opposite of each x value, we write the left-hand side and the right-hand side, implying that which number can you assume that is going to be on the left-hand side of 0 on a number line. So let's go with negative 1. And here, the number which we assume to be on the right hand side of x on the number line, let's go with positive 1. Same thing here. Left hand side of 3, we can have 2. Then right hand side of 3, we can have 4. So for us to get the sine of dy dx, we simply get these values and then we substitute them into our derivative. So remember that our derivative is same as this. So if you get this value, which is negative 1, if you put here negative 1, you're going to have negative 4, then minus 12. So your answer is definitely going to be negative. So you don't write anything here, though you placed 0. You don't indicate anything there. Then if you put positive 1 in this answer, you're still going to end up with a negative. So I hope you have seen, here we are having a negative and you're having a negative. So when you're sketching this curve, we are going to first sketch going downwards, and then we flatten, and then since also here we're having a negative, we are going to go downwards. So this is a curve which is going in a unit direction or in a singular direction, and we call this a point of inflation. So let's also test out this x value. If at all you're having 3, if at all we have the left hand value to be 2, if we substitute into dy dx, you're going to have 4 times 8, then times minus 12 times 4, which you're going to end up with a negative answer. That's why I placed here negative, and if you substitute 4, you're going to end up with a positive answer. So since we're having a negative, when you're sketching our curve, it's going to go down, then between this middle part, which you don't feel anything, is going to flatten. Then since we're having a positive, the curve is going to rise. That's how we find nature of the turning points. So one of them is going to be a minimum turning point, and the other one is a point of inflation, simply because it's going in one direction. So according to what you have explained, this is going to be the sketches. Everything has been explained. So point 1 is going to be a point of inflation, simply because the curve is going in one direction, it's just sloping. And this one is going to be a minimum, simply because the curve is making a turning point, which is at the bottom, so it qualifies to be a minimum stationary or turning point. Now let's also see the use of second derivatives in determining the nature of the curve. So if at all we find that after substituting the x value, our second derivative is going to be less than 0, then we are going to assume that this is going to be a maximum point. But if at all we substitute for the value of x and then we find that our second derivative is greater than 0 or is positive, then this is going to qualify to be a minimum point. And then for point of inflation, always our second derivative after substituting for the value of x is going to be 0. In other words, you are neither going to get a negative or a positive answer. That means that we shall make a conclusion that such a point is going to be a point of inflation. So proceeding, let's look at the next example. So in this example, you are being told that to find the coordinates of the stationary points on the following curve. So if you're having curve defined by this, we are going to be using second derivative to determine the stationary points of that curve. Now remember that I told you when you're having a polynomial, when you're finding the derivative, we write it as a prime. So this is our polynomial. After finding the derivative, we put a prime symbol on top of that polynomial to show the examiner that we have found a derivative. So the derivative of this function is going to be 3x squared minus 12x, then minus 15. And then you make our assumption. You must include this assumption when you're writing your work, that at turning points, always the derivative must be equal to 0. So we simply get our derivative and then equate it to 0. Since it's a quadratic, we solve it using factorization method. So you're going to end up with two values of x, one to be 5 and the other one to be negative 1. Like earlier said, you have to get the corresponding values of y, but in this case you're having polynomial of x, and that's going to act as our y. So you have to substitute for the two values of x to find our corresponding value of f of x. So when f is equal to 5, or when x is equal to 5, f of x is going to be negative 99, and f of x here is going to function as our value of y. So one of the turning points is going to be 5 and negative 99, and the other turning point is going to be negative 1 and 9. So we are going to find the second derivative, and then we substitute for the values of x, and then we see which one is going to give us. We say that if at all is greater than 0, it's going to be a minimum point, and if at all is less than 0, it's going to be a maximum point. If at all the second derivative is equal to 0, we said it's going to be a point of inflation. So our stationary points are this and that. So we'll get the second derivative, differentiating for the second time our first derivative. If we differentiate the second time, we are going to end up with 6x minus 12. Then we bring in our points to test them out, and then we'll substitute for the values of x. So if you look here, if you substitute for the value of x in the second derivative, we have got 18. Now since 18 is positive and is greater than 0, we assume that this one is going to be a point of minimum, a minimum turning point, simply because it's a positive answer. That's how we use second derivative in differentiating between the stationary points that we must have attained. Now let's also test out the other turning point. So for this point, -1 to 9, substituting for the value of x, which is -1, we have got -18. And since this one is negative or is less than 0, we consider it to be a maximum point, according to the assumptions that we made. Now, assuming that you have understood that fully, so let's have an assessment to test our understanding. So you simply have to pause the video and then you take down this assessment exercise. So it's going to be 6 assessments or 6 items or 6 scenarios. Make sure that you put all of them down and then you discuss them intensively for you to fully understand this topic. This topic is very important because it ties back to curve sketching, which you are going to look at as a full topic also under this very differentiation on this channel. So make sure that you like the video, share it to your colleagues, and make sure that you discuss these numbers fully and understand the concept properly. So this is going to be the last assessment under that. Then we proceed to the applications. We proceed to the applications of differentiation or applications of maximum and minimum, where we can apply maximum and minimum in the daily life. So proceeding, let's look at applications of maximum together with minimum in handling practical problems. So you're going to first make a note that these are going to be situations where we need to apply the idea of maximum and minimum in terms of gradients to solve daily challenges. So example 1, we are being provided with a right angled triangle, which is in the form of ABC. Now the moment you see right angled, that means that there is a component which is going to require you to use Pythagoras theorem. So the length of AB and BC are going to vary, so that their sum is going to be 6 centimeters. So if you get AB, which is our height, and then BC, which is our base, their sum must be equal to 6 centimeters. So part A, or item 1, we are going to find the length of AB. If we're told the length of AB is 6 centimeters, we are going to write down in terms of x the length of BC. So know that we are going to, since the length of BC wasn't given, we may give it any letter. So the sum of x and y must be equal to 6. So we simply just have to make the length of BC the subject. Then part B, we find the maximum area of the triangle ABC. Now note the word they used maximum. So we have been looking at minimum and maximum turning points. Whenever we are using these words, minimum can also be least, and also maximum, which can also be greatest. Whenever we are using these two items or these two terms, we always have to get the gradient, and the gradient must be equal to 0. So here they're talking about area. That means that you have to get the derivative of the area, and then we equate it to 0, since it's maximum or least or greater or minimum. So if you look at part A, For part A, we just had to sum up the two sides and then we equate it to the sum, which was 6. Then if you make length BC the subject, we shall get length of BC to be defined as 6 minus x. Now area of a right-angled triangle is going to be, answering part B, area is the same as a half base height. Now note that we cannot differentiate when you're having two variables. And what do I mean by having two variables? You cannot differentiate when you're having height together with base. So for this case, we are having only one term, which is x, and that's why we are going to differentiate. Though we are going to look at that more in details in the following examples. So if you look at here, area, half times base height is going to be x times this bracket. So if you open up the brackets and you simplify everything, we separate all variables, we are going to end up with 3x, then minus half x squared. Then from here, we are going to have to get the derivative, since they talked about area being maximum. So getting the derivative or the gradient, which is the same as the dx, we differentiate area in respect to x. So we get this expression and then we differentiate it. It's going to be the same as 3 minus x. And then we bring in our assumption that for area to be maximum, the derivative must be equal to 0. That's why we saw that here we're having 0 being equal to 3 minus x. So we make x the subject and x is going to be equal to positive 3. Now we have to test out this value, the value of x. Is it going to give us a minimum or a maximum turning point? So you have to get the second derivative and then you substitute for it. So since we are getting a negative answer, that means that this x value is going to form a maximum turning point. And therefore you conclude that therefore the maximum area is going to be equal to this max, means that area that is going to be maximum. So you get the formula of the area which is already up here, and then you substitute for the maximum value of x that you have got, which is 3. So it's going to be half times 3 into 6 minus 3. Putting everything in the calculator, you're going to end up with 4.5 centimeters squared. And that was the answer which was required. So proceeding, let's go to another example. So in this example, we are being told that 1000 meters of fencing wire is to be used to make a rectangular enclosure. Now since here they gave us the sum of the wire that is required, that means that they're talking about perimeter. And they talked about rectangular enclosure, that means that they're talking about perimeter of a rectangle. So you're required to find the greatest. I hope you are seeing this word, greatest. So for anything like greatest or maximum, we have to get the gradient and you have to equate it to 0. So you have to find the greatest possible area and then the corresponding dimensions, implying that after getting the values of x, you also get the corresponding values of y. Now let's look at the solution for that. So first, we are going to make our sketch. The total summation that you're having is 1000. So this is going to be length and width. But remember that perimeter of any rectangular area or rectangular formatted shape is twice length plus width. So 1000 is going to be equal to twice length plus width. So we have to make either L or W the subject, simply because we need to differentiate, and in differentiation we can't have two variables. So we make either length or width the subject. So if you open up brackets, if you divide through by 2, you're going to get 500, and then we take W this side and then you make L the subject, we end up with 500 minus W. So from here we get area, but remember that area is the same as length times width. So after getting length times width, our length is the same as, now remember that length, we have already got it as 500 minus W. Now why do we do this? Remember that area is equal to length times width. And why are we differentiating area? Because they talked about greatest area. So the thing that they attach to either greatest or minimum or maximum is what we differentiate. So they said greatest area. So we have to differentiate area. But if you look at the formula of area, it's in terms of L and W, and both of these ones are neither of them is constant. They all vary. So we have to make this area formula in terms of one single variable. And we have already got our L to be the same as 500 minus W. So we substitute for it here, and then we expand. the brackets to easen up our differentiation. So we shall end up with 500w minus w squared. So since from here we can differentiate this, so we have to get the derivative of the area, since we only have one variable, w. So we have to get dA. We are differentiating a in respect to w. That's why we wrote dA dw. If you differentiate 500w, you're going to end up with 500. And if you differentiate w squared, you're going to end up with negative 2w. Then we bring in our assumption that for area to be greatest, it has to be equal to the derivative, or the gradient must be equal to 0. So 0 is going to be equal to your derivative. And then you make w the subject simply by bringing 2w this side and then dividing through by 2. So your w is going to be equal to 250 meters. Now we also get the value of L from this formula, and it's also going to be equal to 250 meters. Now this step is optional, testing out the W that you got, or the dimension that you got of 250 meters. So since it's a negative answer, that means that it qualifies to be a greatest value, just like the question or the item had determined. So you have to get our greatest area. So greatest area is going to be equal to 250 product of length times width. So 250 times 250, you end up with 62,500 meters squared. And then we have already got the dimensions to be 250 meters together with by 250 meters. And then you make a conclusion for that. Now let's look at another example. Now for this next example, you're being told that a rectangular sheep pen is to be made out of a total, which is the same as perimeter, 1,000 meters of fencing. But for this fence, there is an existing straight edge. So according to that sketch, an existing straight edge is going to be like this. For example, you may have a fence at home, and then what you want to construct is going to be a habitat, but you only have to place your width together with the length together with another width. So this is what you're having. So one of the width, we are going to name it as W, and then the length we name it as W. But remember that for us to get all this total of the perimeter, we have to add up the sides. So here perimeter is no longer twice into length plus width, simply because one side was already catered for. So it's going to be W plus W and then plus L to get this total perimeter. So total perimeter is going to be W, L plus W plus W. But our perimeter or our summation is the same as 1,000. So this is going to be L. If you make L the subject, L is going to be equal to 1,000 minus 2W. Now here they talked about maximum area. That means that you have to find the derivative of the area. And since it's maximum, you have to equate that derivative to 0. So area is given by length times width, but you have already said that we do not differentiate when you're having two variables. We need our area to be in terms of one variable. Now since we have already made our L to be the same as 1,000 minus 2W, we substitute for it. Opening up the brackets, we are going to end up with 1,000W, then minus 2W squared. So from here we can find the derivative. Derivative of 1,000W is going to give you 1,000. And the derivative of negative 2W squared is going to give you negative 4W. Then from here we say that for the area to be maximum, then the derivative must be equal to 0. You must include that assumption. For area to be maximum, then its derivative, which is the dw, must be equal to 0. So we get our derivative and we equate it to 0. So we make w the subject and we end up with w. By taking it this side, it's going to be 4w is equal to 1,000. So you divide through by 4, you're going to end up with your w to be the same as 250 meters. And then your L, we get the formula of L and then it's substitute for w. So L, we shall find out is going to be 500 meters. So from here you can test out this if you want. But what we need to get is going to be the maximum area which is possible. So we simply say that a maximum or a greatest is going to be the same as length times width. Our length we have got it as 500, our width we got it as 250. So you're going to end up with 125,000 meters squared with the dimensions that we have already attained as 500 meters together with 250 meters. So for the next example, we are saying that a closed rate circular cylinder of base radius r centimeters and height 8 centimeters has a volume of this. So we are supposed to show that the total surface area of the cylinder. Now remember that the cylinder is in this format. So we are supposed to show that the total surface area of the cylinder is given by this. And after that, we find the radius and height which can make the surface area a minimum. Now remember that since they're talking about surface area to be minimum, that means that you have to differentiate surface area and then we equate it to 0. So looking at the solution, now the reason why they give us these values, according to the previous examples that you have seen, they give us the known values to help us make one variable in terms of the other. So if you look at the formula of volume of a right cylinder, is going to be the same as pi r squared h. So we're having two variables here. Pi is a constant, but you're having a variable of r and you're also having a variable of h. So since we're having two variables, r and h, or radius and height, we have to express one in terms of the other. And that's the purpose why they give us known values. So they have already told us that volume is the same as 54. This is not 45. It was supposed to be 54 pi. So we make either h or r the subject. So in this case, I made h the subject. Making h the subject, we got 54 divided by r squared. Now we proceed to show that the total surface area of the cylinder is given by this formula. So if you look at this formula, it only has r without h. So we pick our logbooks and then we get the formula of the surface area of a cylinder. So the first formula is going to be for the body, and then the second formula which we add on is going to be for the surface, which is in terms of a circular shape. That's why you're saying plus 2 pi r squared. Now since in the proof that you are showing there is no h, we substitute for h. So simply get the h value that you got as 54 divided by r squared, and then you put it in the formula. Then the next thing is going to be simplifying. So 2 times 54, you're going to end up with 108. 1r goes away with 1r, and then we end up with the required proof. So we have already shown that the surface area is given by this. So if you look at this surface area, we only have one variable, which is r, because pi is a constant. So we are free to differentiate our surface area. Now why are we differentiating the surface area? Simply because they talked about surface area being minimum. And we say that any word which has been attached to conditions of minimum and maximum, or greatest and least, is what we differentiate. So you have to get the derivative of the surface area. So first I'm going to make my equation linear. If I take r up, it gains a -1 as its power. Finding the derivative in respect to r, I'm going to get this. Taking back r in the denominator, I'll have that. So since I've already got the derivative of my surface area, then I'm going to bring in a condition that at minimum, or for surface area to be minimum, its derivative must be equal to 0. So we get our derivative and then we equate it to 0 after writing that assumption. Then from here we are aiming at making r the subject. So simply here we multiply it out. So you first take this one, you first leave one on the other side, and then you take the other on the other side, and then you make everything linear. So you're going to end up with 4 pi r cubed being equal to 108 pi. We cross out pi and then we divide through by 4, we end up with r cubed being equal to 27. So finding the cube root of 27 is going to be the same as 3 centimeters. So since we have r, we can get the formula of h, and then we find the corresponding value of the height of the cylinder. So it's going to be 54 divided by 3 squared, which is the same as 54 divided by 9, and you're going to end up with 6 centimeters. Now this one is optional. So simply, since we have got our radius and our height, we can make our conclusions that therefore r is going to be equal to 3 centimeters and h is going to be 6 centimeters for them to give us a minimum surface area of the cylinder. These derivative tests were done to make a proof whether we are having a minimum surface area. I hope you know that. So since we got a value which is above 0, then the surface area proved to be minimum, like the question says. But the test is optional, you may leave it out. Now let's look at the next example. So this example also writes circular cone. So for this case, it's a cone. This one was a cylinder. So here, there are a lot of times majority of you students confuse formulas of a cylinder together with a cone. So you need to be very careful. You're always provided with the logbooks. Make sure that you pick the formulas from there. So here we're having a right circular cone to be made such that its slant height is going to be pi meters. So we are supposed to show that the maximum volume of that cone is given by this. So let's look at the solution. So if you look at that question, our sketch is going to be according to the following cone. So we're having our h, which is a variable, and our r, which is a variable, and the pi is always constant. So if you look here, remember that we have to express either the radius in terms of h or the h in terms of radius. And how are you going to do that? So since it's a right circular cone, we are going to use Pythagoras theorem. And according to Pythagoras, pi squared is going to be equal to r squared plus h squared. So we either make r squared or h squared the subject. So for this case, I made r squared the subject. R squared is therefore going to be equal to pi squared into minus h squared. Now we pick out the volume of that circular cone. So we get the volume of a cone simply by getting a third pi r squared h. Now we have to differentiate this volume simply because they talked about it being maximum. But you cannot differentiate when you're having two variables, r and h. So you have to make it uniform. So since r squared is the same as this in terms of h terms, we substitute for it. So if we substitute for it and then we open up brackets, we try to simplify, we are going to end up with pi over 3, which is a constant, into pi squared h, then minus h cubed. Then from here, we can differentiate. We leave constants untouched according to the first video, and then we differentiate the variables. So differentiating h, you get 1. That's why you ended up with that. Differentiating negative h cubed, you end up with negative 3h squared. After differentiating, we bring in our assumption that for volume to be maximum, then the derivative in respect to h must be equal to 0. So after doing that, we make h the subject. And making h the subject, we're going to end up with it being pi over root of 3. So after doing that, we get our formula for volume, which is this, and then we substitute for the value of h. Substitute for the value of h there, you're going to end up with volume to be equal to pi over 3 into pi squared, then minus pi squared over 3, then times this h, which is here. And then simplifying LCM and simplifying everything, we end up with the required proof that was required in the question. So I hope that has been understood, and make sure that you address the concerns in the comment section. Now let's look at the assessments that may help us discuss and grasp the content that you have studied in this video. So ensure that you pause the video and then you take the following items. You make sure that you discuss and answer fully. If I tell you don't discuss properly, ensure that you share the video to your colleagues so that you can discuss as a team for easier understanding. So you pause the video and then you take down the items. So this is going to be the end of the assessment together with the end of maximum and minimum as a subtopic under differentiation. I hope you have understood and you discuss fully to your colleagues who are in boarding section or who are in access of this channel to fully understand the concept too. So that was it for this video. We meet in the next session. So make sure that you like the video, share it to your colleagues, and subscribe the channel. See you in the next video.